Hello everyone, this is the fourth in a series of videos covering chapter 16. So we are going to cover the rest of the chapter today, just sections 16.5 and 16.6. We are not going to go in depth on the derivations for the formulas, although the textbook does provide the detailed derivation for them, which it's sort of based on a calculus approach, so it's not really part of the essentials of this course. I consider the derivation supplementary, but if you do have the time, they're worth a look at just to see how they arrive at the formulas through some neat math arguments. Nonetheless, 16.5 is talking about the rate of energy transfer for waves, and we already said that a wave is a transfer of energy through a medium, not matter, but energy. And we might not be convinced of that, right? Where is that energy? Is it really energy? Well, here's a little thought experiment. Let's say you have a string tied to a wall and a free end. You shake the free end, sending a little pulse down to the right. Also, the string has a block hanging off somewhere along the string. And as a pulse passes through it, the block lifts up. So if the block lifts up, and we know the mass of the block, then it must be that the potential energy of the block must increase by however much vertical displacement it had, right? So you could see how far it went up from its rest position, and that means that work was done on it, which means that it received the energy. And where did that energy come from? Well, it came from the pulse that you sent. But we are going to be, talking about waves as continuous pulses. So we're more interested in how they're consistently delivering energy through the medium. So rather than just looking at the energy from a single little pulse, we rather talk about the rate of energy. And that, of course, depends on the energy, on the shape of the wave and the type of wave. So we're going to specifically have a formula for the sinusoidal wave on a string. And what this tells us is essentially how much power the wave delivers. And again, power is a measure of energy per unit time. So you can imagine, right, as the pulses of the wave move through, right, there's a constant amount of energy being delivered. After all, the wave does move with a constant speed through that particular medium. The formula for power, again, that's in units of watts, which is the same as 1 joule per second. So note the formula then requires us to know the linear mass density of the string here, mu, the angular frequency of the wave, the amplitude of the wave, as well as the wave speed. So the first and last terms are properties of the medium, while the angular speed does also, the angular frequency omega is also inversely proportional to the wavelength, right? Because of the wave formula, right? Because of this formula here, which you are used to probably seeing it using the linear frequency, right? F over lambda. But still, right, since the speed's a property of the medium, in some ways the angular frequency varies inversely with the wavelength. Nonetheless, though, for the purposes of this formula, the power does increase with the angular frequency, since a wave with a high angular frequency compared to one with low angular frequency has its crests closer together, which means that although a single wavelength, consecutive wavelengths of a wave with high angular frequency are close together, and as such, as the wave moves, it's transferring a lot more wavelengths in a shorter amount of time than a wave with a longer wavelength. In other words, it's delivering energy faster. The idea also that power is proportional to the square root of the amplitude of the wave, you might recall them from a spring block system. We knew that the total energy for the mass oscillating was equal to 1/2 ka squared, right? So the more it vibrated about its equilibrium position, the more energy it has. So it's a similar notion here, with the proportion that the power is equal to the square of the amplitude. And with the last term, the speed of the wave, right, makes sense that the faster the wave travels, the faster energy gets to some particular point. Then leaves us with the first term in front, the mu, right, the linear mass density. And this two terms actually might remind you of kinetic energy for a single mass, right? 1/2 m. Well, there's v squared. So this is saying that you're sending a wave through a denser string, then that wave's gonna deliver power at a faster rate than a lighter string. You can think about this due to the fact that things, if you have two objects moving at the same speed, but one is heavier, the heavier object is going to have more energy, right? It's going to have more kinetic energy. It's a similar notion in this formula as to why the power is proportional to the linear mass density. String with more mass will carry more energy. Overall, though, although this formula is for the sine wave, the power for any wave is actually proportional to the square of the frequency and the square of the amplitude. So we'll see this is also going to be true for sound waves in the next chapter. So again, this is kind of showing you one way to think about how the wave delivers energy is that if you split the wave up into a series of pulses, a series of wavelengths, then each wavelength carries a set energy, E lambda. So as the wave moves to the right, all this energy passes through a point. And if we had a wave that had a shorter wavelength, then due to the wave formula, that will mean that they'd be a lot closer together and thus moving at a higher frequency. So when they're all bunched up like this, still moving at the same speed because it's the same medium, then because they're all closer together, they're passing a point a lot faster, so they get to move, deliver their energy at a faster rate. And hence that relationship between P and omega squared. So for this is a little quick quiz question. We're told that we have a wave traveling along a string, and we want to ask, okay, which of these things is most effective at increasing the rate at which energy is transferred? So it's not saying that only one of them increases the rate, it's saying which one's the most effective. So let's look at them one by one. A says to reduce the linear mass density of the string by 1/2. So if we do this, if we just look at the formula, we might think, okay, looks like we're linearly proportional to the mass density, right? We might think, okay, this is a relationship. However, that's not true because there's a term for the speed at the end, and we know that the speed is inversely proportional to the square root of the mass density. We saw this in section 16.4. In other words, then it turns out that the power is actually proportional not to mu, but rather to the square root of mu. So if the linear mass density gets reduced by half, then the power, the energy being delivered, actually drops by a factor of the square root of 2. So that's not good. Then B suggests, okay, let's double the wavelength of the wave. So this might be useful because doubling the wavelength affects the angular frequency, but remember that they're actually inversely proportional. Since the speed is still the same medium, the speed remains constant. So by the wave formula here, if the wavelength increases by a factor of 2 to keep the speed constant, then the angular frequency decreases by a factor of 2. So given that the power is proportional to the square of the frequency, then that will mean that the power decreases by a factor of 4. C suggests doubling the tension in the string. So what's the relationship between the tension and the power? Well, again, there's this linear relationship between the power and the speed of the wave, which we know from section 16.3 is proportional to the square root of the tension. If we double the tension, we then increase the power by a factor of the square root of 2. Well, so far that's actually the biggest increase we had, but then D suggests doubling the amplitude of the wave. The amplitude of the wave is actually has a square proportion with the energy and the power. So, well, you see from the formula that the power is proportional to the square of the amplitude. So if the amplitude increases by a factor of 2, power increases by the square. And so far, this is the biggest increase from all the options, so we pick option D. The following example is, again, the same with the quick quiz. It's all in the chapter in the textbook, but we wanted to discuss the problem-solving approach for power. This question basically gives you a bunch of information about the string and what the frequency of the wave being sent through and the amplitude. So it gives you everything you need to know to calculate the power. So we don't know the speed, but we know because we're on a string, we can find the speed based on the tension and the mass density, which kind of, you have a hint here, right? When you're given the tension, that gives you a hint that you probably have to find the speed with the formula from 16.3. Everything else from the formula is given to you straight away, so you're plugging in going forwards. Now, there's actually one more thing that's not given to you straight. You're given the frequency, right? You're told what the frequency is, but the frequency here, right, in 60 hertz, that is not the angular frequency, right? The angular frequency is measured in radian hertz or radians per second. So this is telling you, the linear frequency f. We had to calculate the angular frequency first. So we'd multiply 60 hertz by 2 pi. You get 120 pi radians per second. By the way, the radians is not a real physical unit. So a radian is not actually like a measurement, like a meter, like a meter or a liter or a gram. But there's still a distinction between something being in radians and not being in radians, like angular frequency and regular frequency. So here they show you what they do. They just plug everything in once. And in the second part, they have a little tricky approach to it, a little trick where you're asked to find the amplitude given the power, and essentially you could take the formula and isolate for amplitude, but what they do here is they take the ratio from the new power of 1,000 to your old power, your answer from the last part, and because everything else is constant, you essentially get a ratio between the powers and the amplitudes. So it's a bit of a simpler math equation to solve. So last section, basically the wave functions in general all obey the wave equation. For these linear functions that we've been discussing so far, right, pulses moving through a string, and also in the next chapter we'll talk about longitudinal waves, then they all also must obey the wave equation. In this case, it becomes a linear wave equation. So it has different forms, depending on what type of wave it is. But you see how it's a second order differential equation. And if you plug in, right, the one we had for the sinusoidal wave, where you have, the A sine kx minus omega t, if you take the second order derivative with respect to x and plug this in the left side of the formula, and then do the same with the second order derivative with respect to time, plug it in, you'll see that both sides will equal each other. So this formula obeys the linear wave equation, as we would expect. And any wave function that's a solution to the linear wave equation can be called a wave. The linear wave equation, as is, actually holds a lot of information about the motion, since it talks about the spatial component of the wave in relation to the temporal component. So what we have right on the left-hand side is a second-order derivative with respect to x, right? And in the case of the sinusoidal equation, x talks about the entire span of the string. So this left-hand side is, a spatial component, and basically it relates that to how the wave moves over time. So, and that's the right-hand side, right? We had this term here for how the vertical position of the medium changes over time. So we have a temporal component on the right-hand side. And right, these two are connected together after all, because when we were talking about the sine function, right, we had to specify, okay, which part of the medium and at what point in time, because a pulse moves through any point in the medium. And from this, you can actually use this linear wave equation. Once you found the solutions, once you have a wave function y, you can actually use this to get a formula for the wave speed. So you could solve for this. You could solve for p squared for the sinusoid, and you could get the formula we've seen in section 16.3. And it's not just the sinusoid. There's many wave functions that are also linear that also describe a transverse wave that can be used that satisfy the linear wave equation. So the equation, though, has actually a more general form that can be applied to any kind of wave, both transverse or longitudinal, or both mechanical or electromagnetic. What all those terms have in common is that, again, there's a spatial component on the left, a temporal component on the right, and also there's always a term right here that accounts for the speed of the wave being constant. So the form that the linear wave equation takes for waves on the string is what we have here on the slide, which y in this case represents the vertical position of the elements of the string, right? So y talks about how the elements move up and down. For a sound wave, for a longitudinal wave, rather than having y, the function talking about the vertical displacement from equilibrium, for a sound wave, then the wave function y actually talks about how the air particles or the gas particles vibrate left and right as the sound wave moves through them. So rather than talking about oscillations perpendicular to the wave's propagation, the wave function for a sound wave talks about the oscillations of the medium that are actually happening parallel to the propagation of sound. And for electromagnetic waves, the wave function, again, the linear wave equation is not just going to be called a wave equation. It's going to be a more general form, but still it's it's still a general idea, it's the same. But now the wave function for an electromagnetic wave, rather than talking about the displacement of the particles in the medium, it actually now talks about the electric and magnetic field components and how they oscillate as the electromagnetic wave propagates. So there's a few popular linear wave equations that obviously, so there's a few popular linear functions that all obviously satisfy the wave equation. We already seen the sine one in this chapter. And if you're an electrical engineer or doing signal analysis, you'll probably work with the remaining three in this graph, the square, triangle, and sawtooth waves. For all intents and purposes, the sine will be the most common wave function we'll work with for the remainder of the course. Just know that there's many waves, there's many functions that satisfy the wave equation and describe some sort of pulse moving through. Otherwise, this is the end of chapter 16, and I hope you join me next time for chapter 17, where we'll be talking about sound waves.